Speaker is, it is pleasure to introduce Dr. Sunny Zafar, who will be speaking on manufacturing and recycling of advanced structural composites using microwave energy. Dr. Zafar research interests include microwave materials processing, surface engineering, experimental tribology, advanced welding and manufacturing processes, materials characterization and the mechanical behavior of materials. Sir earned his PhD in mechanical engineering from IIT Roorkee in 2016, where his thesis focused on the development of nanostructure wear-resistant surfaces through microwave cladding. He also holds an MTech in mechanical engineering with a specialization in welding engineering from IIT Roorkee and a BTech in mechanical engineering from Punjab Technical University. Sir talk will delve into the innovative use of microwave energy for the manufacturing and recycling of advanced structural composites, a topic that promises to offer valuable insights into modern materials processing techniques. So, sir will be joining online for this.
Yeah, so thank you so to deliver manufacturing and recycling of advanced composites using microwave energy. At the outset, I would like to thank the organizers of this important conference, especially Dr. Singh, who has been pursuing this conference since very long time. So I'm basically presently working in IIT Mandi as associate professor in the School of Mechanical and Materials Engineering. So before we go into the details of the topic, so I would like to have acknowledgements to my students who have worked extensively on these topics and my colleague Professor Venkat Krishnan, who has supported me a lot in working on recycling part. So many of you may be knowing about IIT Mandi. I'll just take a minute to introduce to people who don't know about IIT Mandi. So IIT Mandi is one of the second generation IITs. So this IIT is located in the district of Mandi in Himachal Pradesh. And the campus of the institute is spread over 520 acres in these forested hills of Kaman Valley in near the Mandi town. So we have this very picturesque campus, and we have the campus situated at an approximate altitude of 3,000 feet, which is the only IIT into the mid Himalayas here in India. And from here, we are working on this area of designing and manufacturing composites for advanced structural applications. So in my talk today, I will be just going through this overview about composites, largely what is the application, and then how we are actually manufacturing the composites using microwave energy, and also how the microwave energy has been utilized to basically recycle the structural composites and how we have recovered back the fibers. So that will be the brief outline about my talk. So as we all know that composites, just a little bit of background, composite materials we know are consisting of two or more materials which combine macroscopically. And the combination of these two materials at a macroscopic level, it yields several useful properties, which are of course very unique to the combination. And composites, they offer a lot of advantages like high damping property, long service life, and several improved mechanical properties like stiffness, flexural strength, impact strength, corrosion resistance, and so on. So here we are talking about advanced structural composites, and we all know that in advanced structural composites, the choice of reinforcement is mostly restricted to glass fiber and carbon fibers. And if I talk about the matrix, so popularly epoxy and combination with any hardener is the choice of material as the matrix here. And utilizing the combination of these reinforcement and the matrix, and then applying heat or pressure using different means, we are able to generate several components as shown here in the slide. Now, these type of components, they find wide applications in several sectors, which include aerospace sector, not only commercial, but also military aircrafts. The renewable energy, especially the wind turbine or the wind energy, utilizes several composite materials to make the blades of these wind turbines, which are very huge blades. And as we are progressing in development of new materials and manufacturing processes, the size of the blades are even getting larger. So the other important component or the application of the composites is in the electric vehicles. So nowadays there is a lot of focus on electric mobility, and electric vehicles, they offer a promising solution to the electric mobility. And all the structural parts of the electric vehicle sooner or later will be made up of polymer composite materials, where they will offer lightweight, high strength, along with sufficient passenger safety. And the advantage of utilizing such materials in electric vehicles is that we can have longer battery range, and at the same time, the performance of the vehicle, structural performance of the vehicle is also not compromised. So with these important applications, futuristic applications, we see the basic, manufacturing processes for composite materials. So essentially, the manufacturing processes for composite materials is revolving around what type of the matrix is being selected. So popularly in composites, we use both thermosets as well as thermoplastics. But for structural applications, it is the thermosets which are widely used. And we know because of their permanent crosslinks which are developed upon curing. So they are very good in several structural applications, as some of the applications I just highlighted. So here, in general, for making any composite, we are utilizing these 4 steps, which include impregnation, layup, consolidation, and solidification. So the innovation that we have provided here is in the consolidation and the consolidation step, because in general, any of the manufacturing technique that I just highlighted in the previous slide here, these all utilize heat or pressure in some form or the other. But the innovation that we have brought in here is in the heating part, especially in the consolidation stage, that when we provide heat. So in this case, we are providing heat using microwave energy. So now there are different ways to produce heat, and these are some of the known ways by which we can produce heat. But there is this microwave is also a very popular heating source. So as we know, microwaves are electromagnetic radiations with a frequency over 0.3 to 300 gigahertz. Originally, microwaves were invented for communication purpose. As you can see here, they were used mostly in radar and so on. But for industrial heating purpose, it is some of the frequencies are reserved for the industrial heating, which include 433 megahertz, 900 megahertz, and 2.45 gigahertz. In context of India, it is 2.45 gigahertz, which is allowed to function for the heating purpose. So you can take any microwave manufactured in India, be it domestic microwave or commercial microwave, the magnetron will be functioning at 2.45 gigahertz. I'll come to the meaning of this 2.45 gigahertz in the next few slides, and then this concept will be more clear. The wavelength of microwaves, it is in the range of 1 millimeter to 1 meter, and these are non-ionizing coherent polarized electromagnetic radiations, which can be readily transmitted, absorbed, or reflected, but it depends on what type of material they are being exposed to. So I will discuss some of the classifications in next few slides. And as it is an electromagnetic radiation, so it has both the electric and magnetic field orthogonal to each other. So in this regard, we can see the difference between heating profile with respect to conventional heating and microwave heating. So in conventional heating, as we know, the heat is transferred using conventional sources from the source which is surrounding the target. So there's a big circle indicates the target, and the surrounding these 4 circles, they indicate the source. So in this regard, we can say that heat transfer is dependent on the conventional modes of heat transfer, which is essentially conduction, convection, or radiation. Because of this, what happens, the surface of the material, it tends to be relatively at higher temperature compared to the core of the target material. But in microwave energy, actually there is no heat transfer, rather there is energy conversion. So now this energy conversion is dependent on the dielectric properties of the exposed material. So here the microwaves, which are indicated by these blue waves, come in contact with the material. Depending on the dielectric response of the material, this microwave incoming energy is converted into heat. And this conversion into heat is so rapid that it heats up the material very fast. And because of this, we have significantly observed that there is sometimes an inverse temperature profile. So what I mean by inverse temperature profile is that the core of the material is at much higher temperature compared to the surface, which is exactly opposite what we observe in conventional heating. So this unique heating capability of microwave, along with the speed at which it can heat, offers several advantages in material processing. And here is one use case for advanced structural composites that I am highlighting. So in microwave, we can say that it is energy conversion and it results into volumetric heating. This is another important characteristic of microwave, that it is the whole volume of the material that gets heated. It is very common, if any, like most of us, we use microwaves in kitchen for heating food, and we can observe that in a matter of 30 seconds, a food item at room temperature suddenly becomes so hot that we cannot even consume it. So from there, we can understand how fast microwave heating takes place. So then next question arises, what are the advantages of this microwave heating? So microwave heating is cost saving because it saves a lot of time and energy. The equipment cost relative to other equipment may be relatively lower. And the process also offers volumetric and selective heating. The process is also environment friendly, as no emission, etc. are there. And we can yield a very good quality properties in the materials which are processed. So we understand the mechanism of heat generation in microwave. So essentially in microwave, the heat is generated by either of these two mechanisms, which is polarization and conduction. So polarization basically involves short range displacement of charge. So in this case, all the dipoles which are present in any material, they try to align themselves with the incoming wave. So incoming wave is an alternating wave because it is an electromagnetic wave. And since this frequency at which polarization takes place is 2.45 gigahertz, so this results in approximately 5 million cycles of rotation per second in these dipole molecules. So this high number of rotations in the dipole molecules essentially generates a frictional heating inside the material, which is manifested in terms of heating, or we can say rise in temperature. On the other hand, we have ionic conduction, which is long range transport of charge. And in this case, the oscillation of ions takes place relatively at 915 megahertz, which is a lower frequency. But for sake of our discussion going forward, we will be focusing more on the polarization part, which occurs at 2.45 gigahertz. As I already mentioned, because this is the frequency which is reserved for industrial heating using microwave energy in India. So, as I mentioned earlier, microwaves are basically very selective to the materials they interact with. And this selectivity comes in from the dielectric response or dielectric properties of the material. Some materials, they have a very high dielectric loss factor. So in that case, the interaction is much higher. And in other materials, the dielectric loss factor may be much less. So based on this, interaction of the microwaves with different materials, so essentially materials can be classified in 4 types, which includes transparent materials, opaque materials, absorbing materials, and mixed absorbers. So transparent materials are basically those materials which do not interact with microwave. So microwave can just simply pass through these materials. So all the materials such as Teflon, quartz, ceramics, alumina, etc., they come in the category of the transparent materials. The second category of materials involve the opaque materials. In the opaque materials, we know all the bulk metals are opaque because they reflect microwaves. So as we know, in any domestic microwave also, it is not advised to put in any metallic objects such as spoon or fork, because there is possibility of arcing which can damage the applicator. Third are the absorbing materials. So materials, for example, water, silicon carbide, charcoal, epoxy, all these come in the category of, you see, absorbing materials. So absorbing materials, basically they interact with the microwave, they absorb microwave, and consequently the heat generation is taking place. A very common example of absorbing material, water, it is present in almost all the food items. So that is why all our food items, they get heated in the microwave very quickly. The last category is the mixed absorber, where we have the multi-phase materials, for example, the composites, the polymer matrix composites, or metal matrix, or ceramic matrix. So in this regard, it is either the dielectric behavior of the, say, matrix or the reinforcement will decide in the end that how much heat will be generated. In some cases, it might be that the matrix is absorbing more microwave than the reinforcement, or it can be the vice versa case as well. So I'll just present some case study here, what work we have done in manufacturing of glass fiber composites. All the work has been done on a lab scale to present the demonstration, to demonstrate the capability of microwave energy to develop such composites. So glass fibers, as we know, they are also used in several structural applications. And for doing this work, we have utilized an industrial microwave applicator in our lab, which is coupled to a vacuum bagging system, coupled to this vacuum pump and so on. So for the sake of comparison, we have also developed similar composites using thermal heating or the conventional heating using a thermal oven. And of course, the same vacuum bagging arrangement was connected to the thermal imaging as well. Sorry, the thermal based setup as well. So in this regard, what we have done, we have demonstrated the use of microwave energy to develop composites utilizing unidirectional E-glass fiber in a ply orientation as mentioned here. So it was a symmetric ply orientation with almost 10 plies as reinforcement. The epoxy that we have chosen was bisphenol A with polyamine hardener, and it was mixed in the ratio of 100 to 32 as specified by the manufacturer of the epoxy. And we can see here that in microwave, what we have done is we have performed the manufacturing or say curing here, because this is a thermoset, at different power levels starting 180 watt, 360, 540, 720, 900 and 1100. So at these various power levels, we could also get the cure cycle time, which was of course here measured in seconds. And the experiments were repeated almost 5 times in each case to get the repeatability of the data. The experiment was also conducted using thermal curing at 2000 watt, and here you can observe the cycle time was almost 8100 seconds. So the idea of introducing seconds is because in several cases in microwave, it is a few seconds, a few hundred seconds, what it takes to get the job done. And now to understand the mechanism, how curing takes place when we expose such composites to microwave. So what we have done here is basically we have tried to utilize a vacuum bagging arrangement coupled to a mold which is made up of Teflon. So Teflon is chosen here as the mold, unlike metallic mold chosen in other manufacturing processes, because Teflon is basically microwave transparent. On top of it, we have put in the vacuum bagging arrangement. This is the industrial vacuum bagging arrangement as utilized in other manufacturing processes. In the similar arrangement, the epoxy is brought into as the vacuum is developed in the vacuum bagging arrangement. Now here epoxy is again unique because epoxy molecules are also polar molecules, and polar molecules are very good when they interact with microwaves. So as we know, epoxy is one of the popular matrix used in structural composites, as no byproducts are generated during the curing of epoxy, and it is widely used in several applications. So that was another motivation of utilizing epoxy in this case. And as the epoxy molecules, they interact with the microwave, the curing sets in because the hardener is already mixed in. And because of the volumetric heating or volumetric interaction characteristic of microwave, we could observe that curing can take place in this amount of time, as shown in this table here. So based on this, we also did some characterization of the composites which were developed in terms of the density, theoretical density and void volume fraction. So what we observed that at different microwave powers, that is 180, 360, 540, 720, 900 and 1100, the density was almost comparable to the theoretical density. Of course, every time the experimental density in any process is less than the theoretical density, it is because no manufacturing process is perfect, and there may be some incidences of being some voids or discontinuities inside the composite, which results in a lower experimental density compared to the theoretical density. The void volume fraction was also calculated using this data, and say at optimized microwave exposure, say at 540 watt, so a void volume fraction of almost 3% or less than 5% was observed. So this is similar to what was observed in thermal curing, but what the point I'm trying to make here is the cycle time what was there in thermal curing was very high. It was almost 8100 seconds, and in microwave, say at 540 watt, it was almost 720 seconds. So we can see this fast cycle time has resulted in not only better quality composites, but is also helped in saving a lot of time and energy. So other than this, the extent of curing was also estimated using glass transition temperature. And what we observed at 540 watt cured samples, the glass transition temperature was almost much higher, and glass transition temperature here is basically similar to what was observed in the uncured epoxy. So here is comparison of the cycle time, and we can say that with respect to the thermal curing, that is T2000, at optimized power at say 720 microwave exposure 540 watt, it is almost 11 times less what is observed with the thermal curing. Even we investigated some of the mechanical properties of the developed composites in terms of tensile strength, ultimate tensile strength, and flexural strength. And we observed that better tensile strength was observed at optimized microwave exposure of 540 watt, and it was significantly higher than what even was observed with thermal curing as a conventional manufacturing process. And similar trends were also observed in flexural strength testing. So next we estimated the energy consumption during the manufacturing process, which is of interest to many industries. So of course this was done on a lab scale, but we installed the energy meter in series to the both the applicators, that is the microwave as well as the other thermal based applicator. So we calculated the energy consumption based on the both theoretically, that is multiplying the power and the cycle time, as well as the actual energy meter data. So here we can see that energy meter data with respect to microwave is not even crossing 1 kilowatt in our case, but it was almost 5 kilowatt for the same size of sample developed using thermal curing. So from here we can estimate that by utilizing microwave energy, we can not only save time but also save on a lot of energy costs. But at the same time, we are generating composites with similar or maybe better mechanical properties. So the conclusion of the process that we have here proposed, which we call as vacuum assisted resin infusion microwave curing, has resulted in higher degree of cure. At the same time, mechanical performance was better, and cycle time was also reduced by and energy 11 times. Energy consumption was reduced by 33 times when we compared it with the thermal curing. So next I will talk about how we have used the microwave energy for recycling. So as I've discussed, there are several applications where composites are being used, and their use is going to get even more, because if you look at the compounded annual growth rate on utilization of composites, so maybe in the coming decade or maybe next 5-7 years, it is going to grow at maybe for 6% for carbon fiber and 7% for glass fiber and so on. And the sectors which are widely going to utilize the composites include aerospace, automobile, and wind turbine, as we have discussed earlier. Now, what happens that we are making a lot of products using composites, but what happens once these products they reach the end of their service life? So we are already struggling with dealing with plastic, simple plastic waste, single use plastic waste, and in coming time the waste generated out of polymer composites is going to add more to that problem. So in terms of recycling, we already know that in metals, recycling is pretty straightforward. Like we collect all the scrap, we melt it, we subject it to some industrial casting process, and then we can reuse it. But what to do with composites? So if you look at estimates of 2050 from this research paper, so it is estimated that globally the carbon fiber waste of the order of 483 tons, glass fiber of 2.2 million tons, and approximately this much amount of waste is going to get generated in next 2 or 3 decades. So we need to do something to manage this waste. Presently, what is happening that we are although trying to minimize the waste by reducing the size, reusing it, reducing the waste, recycling process, and repair. But recycling of fiber reinforced plastics or composites is a tricky affair because of these multi-phase properties that we are talking. So we have a fiber, we have a matrix. So how to at least recover one of it? So that becomes quite challenging. And presently, recycling, what is being done, recycling of these type of components or these type of materials is presently done, but most of it goes into the landfills. And because of the landfills, there is huge environmental impact of these landfills, because they are also generating several greenhouse gases and so on. And we know, since these are made up of thermosets which are cross-linked, so they almost do not decompose in the environmental conditions, and they also release several harmful chemicals into the air, but also chemicals may be released in the groundwater and so on, which is going to have a negative health impact on the population. So in this regard, the recycling efforts in FRP have been done in the past, are also currently done using several means such as mechanical, where short fiber are generated by the recycling process on an industrial scale. In this case, basically we shred the composite part to develop these small pieces, but nevertheless we are not able to separate the fiber and the matrix. Thermal methods have also been used to, but they result in reduced mechanical and physical properties, and often installing such a facility is quite having quite heavy investment and has a long cycle time. So pyrolysis and all those processes, they come in the category of thermal based processes. Next are the chemical based recycling, where we have seen that setup cost on they have high setup cost, and on a lab scale they may be able to generate good fibers, recycled fibers with clean surface and comparable properties. Then we have microwave pyrolysis. Some results have been utilized where we have energy efficient process with short cycle time. And combining these two, we have proposed the process of microwave assisted chemical recycling. So what we have done in our process, basically we have combined the microwave action and chemical action together in a hybridized process, which we call as microwave assisted chemical recycling. So in this process, again, we are utilizing microwave energy, but in this case, the chemicals which are used are derived from green chemistry approach, which include hydrogen peroxide and acetic acid. So what we observed once we subject the epoxy, the glass fiber based composites, the same glass fiber which we have manufactured in the previous case, the same samples when exposed to this combination of chemicals and then immersing it for 30 seconds at room temperature and then subjecting it to microwave, a domestic microwave for a few hundred seconds. So we could dissolve the epoxy out and we could recover the fibers back after cleaning it with acetone. So what we have done in this work, we have used microwave power of 700 watt for recycling and exposure time of 3 minutes. With the combination of this ratio of chemicals, that is the green derived from green chemistry approach, which is the hydrogen peroxide and acetic acid. So because here the acetic acid acts as a mild acid, organic acid, while the hydrogen peroxide, it is a strong oxidizing agent. Under the influence of microwave heating, so localized superheating occurs, which basically melts or dissolves the epoxy, and we can separate the fiber from there. So we also proposed this, plausible reaction, how these chemicals under the influence of microwave, they are able to break the crosslinks and epoxy back. And this is already published in reputed journals, international journals. So we also looked at the decomposition efficiency in our case. So we looked at under specialized optimized conditions, decomposition efficiency of approximately 97% was achieved. And we also compared it with the virgin glass fibers, that is the unrecycled glass fibers. So similar type of the TGA results were obtained. So we also conducted the mechanical performance on single fiber test. So like we extract the single fiber and then we conducted the mechanical test to get various insights into mechanical performance, like ultimate tensile strength, Young's modulus, and strain to failure. So at optimized conditions, say RGF 4, 5, 6, we could obtain almost at par properties with the virgin glass fiber. So here comparison was done with the virgin glass fiber, and we conducted the recycling at several combinations which are already published in scientific literature. So we also conducted some scanning electron microscopy on the recycled fibers. So at unoptimized conditions, we observed that epoxy is still present on the surface of the fibers, but at optimized condition, like RGF 4 and 5, so almost clean fibers with no damage were recycled back from the process of microwave assisted chemical recycling. So what I can conclude is that microwave assisted chemical recycling is starting a new paradigm in recycling the fiber reinforced plastics, and with all these attributes, it could be one of the promising processes in coming time. And in context of India, the recycling of FRP waste has to be taken up, as very little work is presently going on. We are already struggling with the single-use plastic, and if we utilize, some industry can utilize this type of process, it can help to create new jobs and promote sustainability, because not only we are recycling back the fibers because they are expensive. And what is not presented in the slides is that the same process has also been utilized and demonstrated to recycle carbon fibers with the same methodology. And carbon fibers are even of more interest to the industry to recycle because they are the most expensive fibers to manufacture. So all these benefits are there. And of course, this is an innovative work, which is a transdisciplinary work between a chemistry person and a mechanical engineer. And you can understand at IITs, using this transdisciplinary approach, we can solve real life problems. So the work we have done is not like, I cannot say it is a perfect work. We have done it on a lab scale. So as of now, there are still the process is not implemented widely on a commercial scale, which has to be investigated further. The technology that we are utilizing is on a lab scale, so of course the investment cost is not that high. But of course, if some industry wants to scale it up, there may be high investment cost, because for commercial scale, large scale microwave manufacturers are not available in India as of now, and there is very limited regulatory framework available, which can be, create certain uncertainty with investors in coming times. But I'm sure by talking on these type of emerging topics, futuristic topics, we can of course overcome these type of limitations and improve the capability of the country to recycle fiber reinforced plastic waste. So this process has actually, we have already filed an Indian patent, and the patent has already been granted to us to on this process. And this process actually had a lot of traction in the media when we first published in 2022. So almost two years back, we published this work in reputed international journals, and from there, several of the these media bodies approached us to just highlight it to the general public. So these are some of the references, which other references being used in the current slides and have been used. And with that, I wind up my talk. If there are any questions, I'll be happy to answer. Thank you.
Thank you, sir.